Okay, before we start talking about a normal curve, we have to talk about what a density curve is. Okay, a density curve is essentially a curve sketched to approximate the data. Okay, no real data that's small enough for you to look at is actually perfectly normal. Most things are going to be approximately normal. Okay, does that make sense? So, keys to a density curve. That's not a very good drawing of a graph. So it's a graph. Here we have our x-axis. Density curves can look in all kinds of shapes. They are above the x-axis and they have an area of 1. Area. The area under all density curves equals 1, aka 100%.
Oh.
That makes sense?
Mhm.
That's that's what a density curve is. Yeah. There's the basic density curve. This is called the uniform distribution. Everything is equally likely. You can see the sketch they have, which is a slightly better normal curve than I will ever draw. Notice how it approximates the histogram. You can use dot plots very easily. The problem with dot plots is sometimes you end up with too many individual scattered points, so the histogram's often better. Stem and leaf plots sometimes work for showing you normality. Okay. Does that make sense for the basics of a density curve? That makes sense for what a normal curve really basic looks like. Let's get specific on what you have to be able to do. From histogram to density curve. Our eyes respond to areas. Okay. So here we've got 6 and below on this density curve. I don't know exactly what it is. Volleyball scores for all seventh grades, vocabulary scores for seventh grade students in Gary, Indiana on some test. We're going to come back to this. Okay. Looks like it averages about 6.5 to 7. So scoring 6 and below, if we put it on a density curve, we'd essentially do this. And we just sketch like that. Okay. We don't need our perfect histogram. There are very good ways of calculating this, which is tomorrow's lesson, but you guys are going to have that. That's a video. Okay. It's actually a pretty simple calculation. Although you might need me to actually physically point at you at things for you for how to use the tables. Like I tried to do it in video, but it might be easier. So here's the things that make a density curve. Always on or above the horizontal axis, the x-axis, and has an area of exactly 1. So this one is skewed left, correct? What we're interested in is the area. The area is the percent of my data that falls between 7 and 8. In this case, 12% or 0.12. Does that kind of make sense?
Mhm.
Okay, question that shows up on random tests. And you'll hear the SL kids complain about this. Middle 50% of your data is between what and what?
Oh, it's between. Hmm, shoot, it's like
Quartile 1 and 3.
1 and 3 something.
The median's quartile 2, yeah. That makes sense. We're going to be talking about percentages that fall within certain regions.
Wait,
Why why do they complain? Because the way the question's worded. It's one of those things that very simple question, but it'll be asked in a way. If you guys remember when you did that mock exam last year, it talked about in the bottom quarter. Well, that's less than quartile 1. And it gave you a 5 number summary or a box and whisker plot. I don't remember. But it talked about things being in those chunks, and it's important to understand the percentages that fall in each part. So, shape. We've talked about symmetric and skewed, right? So, with a symmetric graph, mean, median, and mode are all the center, right? If it's perfectly symmetric. With the skewed one, mode is at the top. Median means there is equal area on each side. Which way do you notice the mean being dragged from the median? So area I'm talking about, which it's pulled towards the end because those have a greater effect, right? Because they're further from the mean. So equal area here for median. 50% above, 50% below. That kind of makes sense? And yes, mode. They don't put mode in this book, but it's important to know. I think it might show up in IB. What does the mean?
Like, I know. That
What does it mean? Okay, we're getting there.
Also, no, what is mode?
Mode is most frequently occurring number, so it's the highest point. What you will hear for sure is bimodal, meaning it has two high points. Bimodal will sometimes look like this. So mean on the graph, did you order, Rowan? Okay. Mean is the balance point. So there's equal like weight distribution. So you guys have done a seesaw, right? Teeter-totter. And you know if you're the lighter person, you have to move back, and the heavier person has to move towards the middle, because that balances out the torque. These things that are further away have essentially more of a torque against it, just like a seesaw. Okay. So that's why it balances at the mean. There's less area on the right side of this one, but there's enough things that are further away to counterbalance it. Okay. So that's a density curve. One of your questions, this is one of your questions. You want to verify it's a density curve? What does the area under it have to equal? 1. That's how you verify. You literally check the area. Now, this density curve, they don't draw in the sides, but it's a vertical line here and here. Okay? Just find the area, make sure it equals 1. The area does not equal 1, it's not a valid density curve. Okay? Now it's time to learn what it means to be normal. Do you guys know what this symbol means?
What's like micro?
It's mu. In statistics, mu is used for micro in when we're doing mu is used for several things. It's coefficient of friction in physics. If you're talking units, it's micro, micrometers, micrograms, etc. In the context of statistics, it means population mean. So, if my population is high school seniors in the United States, do you think it's easy to get the population mean? Probably not. There's a lot of high school seniors, aren't there? And some of them don't regularly come to school. Thankfully, that doesn't apply to this class. This class regularly comes to school. But what if we did like households? It's hard to get a hold of every household, right? And it takes a lot of work. When we'll talk about census. So most of the time we don't actually know this. So that's mu. Sample mean, we're going to be acting like we do for now, but eventually we're gonna get to the point where we use the sample mean to approximate the population mean. Okay. So sample means we took a random sample of, say, 1,000 high school seniors. Do you think that would get us a good approximate of the mean? Good enough. What we're going to do is then, if we use a proper sampling method to get it, calculate how close is close. That makes sense. So we have methods of calculating. So it's close enough. Well, is it close enough? Is it really close enough, or is it kind of? And we'll have ways of calculating, yeah, it is close enough. Okay. And that's all dependent on this normal curve. Sigma, this is lowercase sigma, is population standard deviation. We'll use the letter S for sample standard deviation. So if you remember from chapter 1, we had our two measures of spread. We had interquartile range that goes with median. We have mean and standard deviation as our measure of spread for this. So we're going to be talking about essentially how many standard deviations or how many of our spread are we from the mean? And above would be to the right, below would be to the left. That makes sense? In tomorrow's lesson, we have actually a mathematical calculation that means it's happening. So as you go up the normal curve, it starts by growing more steeply, and then it starts to grow less steeply, and then it's more steep again. And these are inflection points. Who remembers inflection points? Good. There are inflection points. If you really want to get advanced, which we will not do this class, you can integrate the normal curve. It's an area under a curve, right?
I was supposed to find the area. Like pi equals 1.
With integrals? No.
Really? We're not
You-
even doing integrals?
No. No, 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 no. That's way more advanced than this class. You don't know how to do that in level of integral.
Oh,
I don't think I ever have. I think I could. No, it's a gnarly integral.
No, but like for the stuff before, we're talking about like when the area of the curve equals 1. That's integrals, no?
No. You're going to be checking by using like geometry. You could do integrals, but then you'd have to write all the functions. As integrating a normal curve can be done, your calculator can do it for you just fine. We can all thank Gauss for doing it and developing a nice table so we don't have to. Mm-hmm. Yeah. Yep. You can thank your calculator, and there's a table in the front of your book that just has them all, everything you need, all done for you. You just have to look it up. Okay. Now, the 68, 95, 99.7 rule used to sometimes be called the empirical rule. This says 68% of the data, or my observations, falls within one standard deviation. So I'm going to draw a normal curve and show you what this means. So here in the middle, we have our mean. So if our mean was 50 and our standard deviation is 10, mu plus sigma is then 60. So for this example, I'm going to do an example one. Mu equals 50. I'm going to use really easy numbers. Sigma equals 10. These are far from perfect drawings. Let's say this is an ANI test. The mean score was a 50%. Actually, not bad. That's almost a 5.
50% is a 5.
51-ish. On 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 the actual ANI tests you'll take. For overall score when they average them together, and it varies a little bit year to year, but about a 12% is a 2, 12 to 24, 12 to 25 is a 2, 25 to 37 is a 3, 37 to 51 is a 4, 51 to 63 is a 5, 63 to 75 is a 6, 75 and above is a 7. So, this is an ANI test. Mean is 50, standard deviation is 10. That's probably a little small on the standard deviation, but whatever. 68% of kids will fall between one and standard deviation below and one standard deviation above. Does that make, which in the case of the numbers I chosen is between 40 and 60. That makes sense? Devin, that makes sense? What would be two standard deviations off?
No,
95, but what would the numbers be? 30 and 70. Does that make sense how I'm getting the numbers? What's 3? 80 on the right side, 20 on the bottom side.
pretty off.
So calculating those is not terribly hard, is it? 95% of my observations or 95% of my students, if these things were right, would score between 20 and 30. They're 30 and 70. And my final one, 3 standard deviations, 99.7. So that leaves a grand total of 0.3% that fall further than 3 standard deviations away. Okay? Whole grand total of 0.3%.
One middle school something says this.
Yes, you're going to have to get used to these Greek letters.
Like, you say one and also it's
Chinese, so that's.
They're Greek. They don't really look like English. We just have to have good enough writing.
That's fire.
Dylan, that was a we. Me too. I'm included in that. So, one of the keys to this is what it means to be normal. If it doesn't match this, it's not normal. Okay? People go, well, how do you know it? But how is it this time all the time if it's normal? Well, if it doesn't match this, it's not normal. Okay, this is like a definition. That makes sense? This is like the definition of what it means to be normal. Okay, you guys got that down? So, we're going to look at young women's heights. The mean height for young women, and young women is defined in this to be 18 to 24. This is legitimate data from the late 90s, early 2000s. Okay. I'd assume it's pretty similar still. The mean height of young women is 64.5 inches. 5 feet 4.5 inches.
Let's go.
And the standard deviation is 2.5 inches. So what is the mean minus 62?
7.
67. That means 68% of young women fall between 5'2" and 5'7". You're like, actually, that's pretty believable, isn't it? You're not, we'll do young men later. You're 5'7"? You're not 68th percentile, Rowan. Dylan is. So this is, if that's 34%, right? This whole half here is 50%. That's 84th percentile.
Gosh, I'm just so tall. Tall.
Okay.
Oh, yeah.
I would say these are probably a little bit skewed on the tall end too, because I think there's a little bit more women over 6 feet. Because this next one is 69 and a half or 59 and a half. And then 3 standard deviations is 72. I think there's more women over, this is 59 and a half. This is 411 and a half. This is 49. I think there's more women over 72 than over 6 feet than under 4'9". I think it's a little skewed on the tall end, but it's approximately normal. Okay. So, does that make sense how I did that? If we divide all of these chunks up, you're going to say you divide 64 in half. And then you take from these right here, become 13.5. If we take 95, subtract out the 68. This is 34. That makes sense how I'm getting that. I divided 68 in half. This 2 to -2, I take 95, I subtract out the 68 and divide it in half. I get 13.5. This, honestly, usually we're interested in 2 and beyond more than we are 2 to 3. But this 2.5%, this being 2.35. Because if 95 is between -2 and 2, that leaves me with 5% on the outsides, right? Which is 2.5% on each side. I have 0.3 here, so that's 0.15%. And that leaves 2.35%. That makes sense how I'm getting all of those values. They're going to ask you about between here and here sometimes, and okay. And they'll probably give numbers like I did with the 20, 30, 40, 50, 60, 70, 80. And you'll have to figure out where they are. They're like, okay, this still isn't bad, right? You compare this to calculus and you're like, oh, this is a piece of cake. It won't stay this easy, but this isn't too bad. This shouldn't be too bad.
Sure, you just got pictures.
I mean, does that kind of make sense? Men's height is average of 5'9", standard deviation of 2.5. Dylan, you're less than 1 standard deviation below. You'll be able to calculate your percentile after tomorrow.
Actually, I want to know, man. Ignorance is bliss.
Okay.
Bliss.
But that's it for 2.1.
Woot woot.